Join. Okay. Close. This one. I feel like we get fewer people every day. It's not a good sign. I laugh, but it's not a good sign. I hope everybody is on Zoom. We got to chat. Oh, yeah. And it is voting, so do go vote. If you have not voted yet, please go and vote. I voted very early this morning. It's very cold outside, but the line wasn't that long. So, yeah. Yeah, it wasn't too bad. Wasn't too bad. But it makes me too nervous not to go and do it before. Like, like I know I'd be done here about 3 o'clock and we could go, but I just feel like I need to go and do that as early as possible. Okay. So let me move this. Let me move this. Okay. Can y'all hear me? Yeah. All right. So attendance is up. So please go ahead and check in on attendance. I did not think that was appropriate on a day that we were going to get hit with a Category 2 hurricane.
Yeah, I had no electricity, no internet. In fact, still have no internet at home. We got electricity that Sunday night.
Wow.
So.
Wow, and that is one thing I wanted to say. A lot of people who were out of electricity did email me, and if you were out of electricity and you need more time, an extension on a homework, whatever it is, just please tell me.
Okay, yeah, that would be helpful.
Just send me an email. Right, you have no electricity, you can't do it.
I stayed at school till 10 o'clock last night doing work, because if I go home, I can't do it.
That's exactly right. Yes, we're going to do some iClicker today. We are going to do some iClicker. So go ahead and check in on attendance first, and we'll let everybody get in on that. And I'll go over a few announcements, and then we'll do some iClicker. So in response to the hurricane, right, my instructions were, we don't have a regular class, but like you have your chapter 9 videos, so try to watch as many of those as you can, right? So because of the hurricane, what I did was I just pushed us back a day, but that makes some changes on our schedule. So I want to go to our schedule and show you the changes. Okay, so here we go. All right, so this is us today. We are Tuesday. I don't know how to make all this much smaller. I don't know how to do that, but okay. I wanted like this smaller. I just want to see this, but that works. That's good. All right, so we're here on Tuesday, right? What we were supposed to do last Thursday was to start working on the in-class problems, but not a hurricane day thing to do. So what I did was I extended your chapter 8 homework to Saturday, and if you were still out of power, please just let me know and I will give you some more time. No big deal. And today, basically in the schedule, you should have watched all the videos for chapter 9 by now. but it's okay if you haven't, because we're only working on the first half of chapter 9 in class problems today. So it kind of gives us a little bit of a cushion, you know, with everything going on. So Thursday, for next class period, you have no new videos to watch, right? You've watched, congratulations, you have watched every single video, pre-recorded lecture for the semester. Woohoo, right? Give yourselves a round of applause, y'all did great. So what we're gonna do on Thursday is we're gonna work the second half of chapter 9 in class problems today, that day, all right? But that means that we were supposed to have an exam that day. So our homework gets pushed back to Monday and we have our exam on Tuesday. All right. So it gives you the weekend to catch up on that homework, to get studied for the exam, get prepared, right? And then don't forget that your lowest regular exam score is going to be dropped. So if you have an exam score you would like to drop, please put forth the time and effort for this one so that we can drop one of those earlier exam scores. Okay, so make the best of this extra time, please, please, please. All right, so that meant that we had Thursday. With everything going on, I'm sorry, I'm not starting a new chapter. That will be our exam review. So instead of having an exam review outside of normal class time, this will be our exam review. Okay, so start putting together questions. I'll have a little something for us to do, but I'd also like to include your questions on, you know, what you need help with before the exam. So please start putting that together. And then exams. Any questions about the schedule? Good. Okay. All right. And if you have any questions, you can always send me an email. All right. So we did attendance. iClicker questions. Here we go. All right, so like we usually do when we start the in-class problems for one chapter, we do iClicker questions from the chapter before, right? So which one were we on? Let's see, number. No, we did that one. No. I'm clicking the wrong thing. Here we go. Eventually I'll get it, y'all. All right, so I'm anticipating that everybody has checked in on attendance. So here is our first clicker question. Select the most concentrated solution. Select the most concentrated solution. If y'all haven't noticed, we do have a guest today. It's voting day, so schools are closed, so Charles is hanging with us. Oh, and I forgot our joke. I'll do the joke next. Okay, oh, I should have said 10 seconds, so 10 seconds from now, so 1:35. Okay, so when we're looking at these, let's see what we said. Okay, we got a little bit of a thing going on. What is this ppm? Whoa. What does ppm, ppb mean? This is parts, right, per million. Good. And parts per billion. When do we use parts per billion or parts per million? When we have things that are high concentration or low concentration? Very, very low. If I could spell low, very low, right? Usually we express things in percent, but when there's so little of it, then we say it's either a part per billion or a part per million, depending on the concentration, right? So it should have been a red flag for you, right? That 10% is all by itself. If I wanted to convert 10% to parts per something, what do you think that would be? Parts per 100. So now do you kind of see how they're all related? It's percent. I mean, we're used to seeing percent, and you know that percent's out of 100, right? But sometimes you just don't quite think about it that way. But remember that we only express very, 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 very low concentrations as parts per billion or parts per million. Okay. Really, really low. That's right. Okay. So let's try another one. Oh, before I click it, take out your calculators. You will need your calculators. I'll give you all a second to get a, I know y'all gonna make my favorite sound in the world. Clicking up calculators. All right, so, and I missed my joke, so y'all ready for y'all joke? Why did the moon have a bellyache? Because it was a full moon. Yeah, it was a full moon on Halloween. Did y'all see that? It was really pretty. It was a really pretty full moon. All right, so y'all ready? Got their calculators? Here we go. All right, let me move this up. Make sure it's shown. All right, so I'll give y'all 2 minutes on this one. How many moles of potassium ions, K+, are present in 3 liters of a 0.5 molar aqueous potassium chloride? You do need your calculators. Y'all, it's dimensional analysis. Dimensional analysis. You don't have to look for anything. You need to look in the problem. Ah, 10 seconds. All right, come on, y'all, ring in. Thought we had 45. All right, so when you do this, what we're starting with is we know that we have 3 liters of a 0.5 molar aqueous potassium chloride. What does that big M stand for? Moles per liter. That's the concentration, right? So whenever you see big M is moles per liter. So if I have a 0.50 mole per liter, and this is potassium chloride, What do I need to do? I'm trying to get to what unit do I need? Moles. I need to get to moles. So how do I get to moles? Y'all awake today? How do I get to moles? I got to get rid of what's on the bottom? Liters, right? Liters. So I know that I have 3 liters. So what happens to my liters? They cancel. Okay, now you cancel out the liters. That's right. Okay, so now, what are my units? What am I left with? Moles of what? You're right, moles. But this is where a lot of people forget something, and it didn't actually change your answer, but I thought this would be a really great place to talk about it. Moles of what? I have moles of potassium chloride. So now I need to say, in 1 mole of potassium chloride, how many potassium ions do I have? 1. And that's from my formula, KCl. I have 1, for every 1 potassium, I have 1 chlorine. So if I have 1 mole of KCl, that means I have 1 mole of K plus, and I have 1 mole of Cl minus, right? Actually, it's plus, but. So if I had, let's say, magnesium chloride, what's my formula for magnesium chloride? MgCl what? Trying to do a refresher here. Magnesium's in what column on the periodic table? Magnesium's in column 2, right? So it has a charge of +2. Chlorine's in column 7. So it has a charge of -1. So what should my formula be? If I have Mg +2 and Cl -1, what should my formula be? MgCl2. So if I have 1 mole of MgCl2, that means I have 1 mole of magnesium 2 plus. How many moles of chlorine do I have? 2 moles of chlorine, right? Because that subscript is going to tell us, whoa, what happened? Did I stop screen sharing? Y'all, hang on. Exit full screen. Am I still screen sharing? No. Okay, I don't know how I did that. All right, so if I have MgCl2, that 2 is telling me I have 2 moles of chlorine for every 1 mole of my substance, right? If I have KCl, there's 1 and 1, that means I have 1 mole of each for every 1 mole of the substance, okay? So what should you have gotten numerically, even if you forgot to do that? 3 times 0.5, 1.5 moles of K plus. So you should have gotten A. Good. Okay. So even if you forgot that last step, but don't forget that last step. All right. Oh, I'm not doing that one. Doing this one. All right. What is the molar concentration of a lidocaine solution prepared by diluting 5 milliliters of a 1 molar lidocaine stock solution to the mark in a 25 milliliter volumetric flask? Before I start the timer, what formula should we use? Yes. Good. And I'm trying to get the chat back. I'm working on it, y'all. Okay, so 2 minutes. There we go. So that's our dilution formula. You want to use your dilution formula because that's what we're doing. Remember, you got 2 minutes. Okay, 10 seconds. Okay, so when we plug this into the formula, what are we going to get? Our CIs, what does I mean? That's our initial or our stock. So what's our stock solution? We have a 5 milliliters of a 1 molar. So we have 1 molar times 5 mils. And I know my final volume is 25 milliliters, right? It didn't tell me how much water I'm putting. It's telling me my final volume. If I said I added 5 mils of my lidocaine stock solution to 25 mils of water, what would my final volume be? If I did this differently, if I said I want 5 mils of stock plus 25 mils of water, what would my final volume be? 30. But is that what's given in this question? No. It's telling me I'm filling to the mark of 25 milliliters. So that means my final volume is 25 milliliters, right? And I don't know my concentration final. You understand the difference between the two? I a lot of times see people get mixed up there. So be careful about that. So divide by 25. What do you get? You should have gotten 0.2? 0.2, good. Good, yay. All right, I think one, yep, last one. Okay, make sure we can see all of it. Okay, so here we go. Select the correct statement regarding solutes crossing a cell membrane. So think about what can cross a cell membrane. I was waiting until 2 minutes instead of a minute and a half, but I'll give you the 2 minutes. So you have about 15 seconds. Okay, so when we think about things crossing a membrane, let's kind of jot ourselves down some notes. What are some things that will cross a membrane? Something that's non-polar. What else? Something small. Small non-polar will cross. How about will not? Do the opposite. Something big. Now, something polar. So we're going to put medium and we're going to put polar kind of in the middle. But the opposite of non-polar is not polar. I know that's sort of crazy, but it's really not. Non-polar is completely neutral. So what's the opposite of something that's neutral? Charged. Right? Okay. So when we look at our answer choices, this is what we kind of have to remember, right? There are lots of stuff in the middle, but if you remember, non-polar and small crosses, big and charged will not. Okay, so let's look at the top. Let's go by one by one. Magnesium ions are more permeable than small neutral amino acid molecules. What is this? This is charged. And this is small and it's neutral. Neutral is another word for non-polar, right? So this should have been less, right? Charged particles will move less than small neutral molecules. Okay, so it can't be A. B, water molecules are more permeable than sodium ions. This one's true. This one's true. How can water get across a membrane? There are two different ways. Diffusion, but we call it something special. Osmosis. Diffusion is crossing without a membrane being there. Osmosis is that same diffusion, but across a membrane. Okay, or what? It can go through a channel. Not ATP dependent, but just go through a channel. Like a tunnel. What do we call that? Facilitated, F-A-C-I-L. Facilitated diffusion. Yes, but that facilitated diffusion does go through a protein channel, Hayden, that's right. Okay, all right. Sodium ions are more permeable than oxygen molecules. What is this? Small and what? Non-polar. It's two of the same atom. Is that going to be a polar bond? It can't be. It's two of the same atom. It can't be polar. So no, this would be less, right? Proteins are more permeable than glucose, a small polar molecule. Proteins are humongous, right? How many proteins do you have in your cell? I don't know, hundreds of thousands. Why do they stay in your cell? Because they can't leave the cell. What keeps them from leaving the cell is the membrane, right? So that's like the point of the membrane, to keep the proteins in and let other stuff through. Okay, so they're less. Okay, all right, so what do we say? B, good, B. All right. Okay, so let's go do some problems. Let's go do some problems. All right, here we go. Y'all ready? Some acids and bases. So give me a brief, how do we know it's an acid? An acid will what? Donate a hydrogen ion, right? Okay, and it makes a hydronium, right? So what's another way that you could say H plus? You could say it as H3O plus, right? Okay, base. What's the definition of a base? Accepts a hydrogen. Good. Okay, so something that is neutralized by a base must be N. Don't everybody say it at once. Remember, an acid plus a base yields a salt plus water. I remember that from the video, right? So what is neutralized by a base? An acid. An acid. Produces OH minus in water. If I have something like this, and I put it in water, what's going to happen? I make OH minus, so that must be a base. Thank you, gentlemen. A base. It's going to produce OH. Okay. Has a slippery feel. This one's straight from the notes. It's a base, but nobody's going to try that, right? Also a base. Okay, donates a proton. That's an acid. All right, in your own words, explain how in aqueous solution, H plus and H3O plus represent similar things. So if you have something like HCl, let's say, and I put this into water, we know that that's going to completely ionize, right? But are those the only two particles that are inside of your beaker? No, you also have water, right? So water is actually going to react with this H plus ion. What's it going to form? The water is going to actually pick up a hydrogen and form an ion. So water is really cool because water can act as an acid, a weak acid, or a weak base, right? A weak acid is going to do what? It's going to donate our hydrogen, and our weak base is going to accept a hydrogen ion. So what did the water do in this case? It picked up a hydrogen, so it's acting as a weak base. So because water acts as a weak base, we form the H3O plus ion. Yeah? At least I got some head nodding. All right. In each of the following equations, identify the reactant that is an acid, which is the hydrogen donor, and the reactant that is a base, the hydrogen acceptor. So what I like to do when I look at these is to kind of draw a line between the substances that look really familiar, right? So the first one that looks familiar to me is water, and it's turning into something that's not quite water. What did it do? Did it accept a hydrogen or did it donate a hydrogen? It accepted one. Accepted a hydrogen ion. So our substance here that accepts a hydrogen ion is called what? a base. Okay, so then we look at our other substance. What happens to our other substance? So it loses or it donates a hydrogen. The substance that donates a hydrogen is an acid. So all you have to do really is look at the hydrogens. The hydrogens are going to tell you the story. Okay, let's try the next one. We have H2O water, and I see it's turning into OH minus. Ooh, now what's water doing? It's giving up a hydrogen, right? So this is the donor. If it's a donor, what do we call it? This is the acid. So do you see how water is acting as either an acid or a base depending on what other substance is present, right? Okay, so then PO4 3 minus is turning into HPO4 2 minus. So what is this one doing? This one is a base because we see that it is accepting our hydrogen ion. If you can remember donating and accepting acid base, you're going to be okay. All right. Now, I kind of alluded to the fact that water is a weak acid and a weak base. That implies that there are strong acids and strong bases, right? So I will give you a table on your exam resources, but I'm going to teach you some tricks as well, because the amount of time you spend flipping back and forth can be a time sunk. It really can be. So I want to teach you some ways to do it relatively quickly. So let's talk first about acids. So I'm going to come over here and I'm going to write my acids. There are two different kinds of acids. We have binary acids. What does binary mean? Two. Binary means two. So we have two elements, hydrogen and something, right? There are only a few strong binary acids, and you remember them by the little saying, I bring clay. So I, Br, and Cl. So Hi, HBr, H. It's like I can't erase today. HCl. These are our three strong binary acids. Then you have acids that contain more than two elements. So tertiary, T-E-R-N-T, tertiary, that's not right, but tertiary. T-R-I-T-A-R-Y, I don't know. Spelling is not the strong suit. So if you're looking at your strong acids, your tertiary ones are going to have two more hydrogens, two more, come on, oxygens than hydrogens. Okay? So count them up. When you look at your substances, count up your hydrogens, count up your oxygens, and you will know if you have more or less, right? And I want to hide the table over here because I want us to use these words. So which of the following are strong acids? Do we have any binary acids in our list? No. Right up here was the only one that, well, these two were the only ones that were binary. HCl was over here, so it's strong, but HF is not, so it's weak. So none of these are binary. All of these are tertiary. Do I have two more oxygens than O's here? No, because I have one hydrogen and I have 2 oxygens. So I don't have 2 more oxygens than hydrogens. So no, so this must be weak. Okay, HNO3. I have 1 hydrogen, I have 3 oxygens. Oh, yes, I do. So this one is strong. H3PO4. It's weak. So this is my only strong acid in the list. Once you kind of know the rules, it's not so bad. The last trick for acids is if the acid contains carbon, it's weak. We haven't gotten to any of those yet, but we will. Is sulfuric acid just... No, it has 2. H2SO4. It has 2 more oxygens than hydrogens. Does that make sense, Jason? Trying to read what it's saying under the chart. Oh, so when you disassociate 1 hydrogen, that's what we're saying is strong, not disassociating 2 hydrogens. Okay. So which of the following are strong bases? Okay. Now, our bases tend to be in group 1, and there are a few in group 2. The few in group 2 are strontium and barium. So group 1 and strontium barium hydroxides are strong. MgOH2. Strong or weak? Weak. Magnesium's in group 2, but it's not strontium or barium, so it's weak. NaOH, what group is Na in? Group 1, so it is strong. FeOH3, that's a transition metal, right? So that is definitely weak. So you don't always have to go back to the tables. I feel like that just takes up time. All right, so the next thing is thinking about what does it mean to be a strong acid or a strong base? Why do we define them that way? Well, if you have a strong acid or a strong base, like let's say HCl, right? What did we say happens to HCl? You make H plus and Cl minus. This is a complete dissociation. Every single HCl molecule will dissociate into a single hydrogen ion and a single chlorine ion. Every single one. That's 100% complete dissociation. If we have something that is weak, like HF, yes, we're going to make some ions. Oh, that's supposed to be a minus. We're going to make some ions, but really, most of it is going to stay together. So it's weak because it weakly dissociates. Only a small percentage, maybe 3%, is going to dissociate into solution. That's why they're weak. Strong, all of them will, right? So when you're asked which of the following compounds will completely ionize, it's just like asking you, is it strong or weak? It's the same question. Okay, so LiOH, what can you tell me about that? Weak or strong? Lithium's in group 1, so it must be strong. Good, so it's a strong base. That's right. So is it going to completely ionize in water? Yes. Yes. H2O. What did we say earlier about water? It was weak. It was a weak acid, and it's also a weak base. Benzoic acid. What do we see in benzoic acid? I see two what? Carbons. Ooh, carbon containing must be weak. Okay, it's the same sort of question. All right, now we need to talk about naming our acids and bases. When we name our acids, remember there are two kinds of acids, right? There are those binary acids, right? And when we say our binary acid, right, it's hydrogen and something else. So we're going to say that. We're going to say it's hydro, and then you're going to name the element. So this is element. And then you're going to end it in IC, and then you're going to put acid after that. So HCl, hydrochloric acid. HBr, hydrobromic acid. HF, hydrofluoric acid, right? All two elements the same way. Those are super easy to do. Then there are tertiary. Tertiary are going to be more than two elements, right? So that means a tertiary is going to have some number of hydrogens, H's, and a polyatomic. So you go to the polyatomic ion table and you say, okay, my polyatomic, does it end in IT or does it end in ATE? If my polyatomic ends in ATE, my acid is going to end in IC. If my polyatomic ends in IT, my acid will end in OUS. So you can say that you went to chemistry class and got adic-itis. How you remember it? Adic-itis. All right. So let's try some of these. 9.14. We're going to name and write the formula for our acid. Iodide is the iodine ion. So how do I turn that into an acid? An acid always has to donate a proton, right? Donate a hydrogen ion. So what do I need to do? I just need to slap on a hydrogen. So if I have hydrogen and iodine, I'm just going to be HI. All you have to do is add a hydrogen ion. So if I have a H plus and an I minus, what's my overall formula going to be? Just HI, no charge, right? Because the charge is balanced. Now I need to write my name. So I'm going to write hydro. Then I'm going to put the beginning of iodide, but I'm not going to put the IDE. So I'm going to say hydro, iodo, and then I'm going to put IC, so hydroiodic acid. Sounds kind of funky, but hydroiodic acid. Okay. So now perchlorate. Ooh, this is a polyatomic ion, right? So I need to look at my polyatomic ion. It ends in ATE. So what's my acid going to end in? IC. So all I have to do is write the same thing that was there, put a hydrogen on it. So ClO4, what do I need to do? H, ClO4, so there's my acid, no charge. Doesn't mean it's free, but no charge. And how do I name it? Perchlor, right? I'm not going to put the ATE. I'm going to put IC and then end it in acid. You don't put the hydro in front of it. You only put the hydro in front of it if it's binary. So if you got a polyatomic ion, there's no hydro. So my next one, acetate. Acetate's another polyatomic ion, so we don't have to write the hydro. So we're going to write our formula. We have CH3COO, and instead of being a minus, we're going to put our hydrogen on. What does this one end in? ATE, so we're going to end it in IC. So this is what? Instead of being acetate, it's acetic acid. You've heard of acetic acid before, right? This is where we get the name, right? Ever wondered that? Why did we name it that way? That's why. I feel like chemistry explains that a lot, right? It's kind of nice. Okay. Complete and balance the following neutralization reactions. So we're going to have an acid. We're going to add it to a base. What are we going to make? Acid plus a base. We're going to make what? A salt plus water. If you have carbon, you're also going to make CO2, but only if you have carbon. In A plus B, if one of these has carbon, like if you have carbon here in one of these two, then you're also going to make CO2, but only if you have carbon. Okay. All right. So H, let's do this one. HNO3 plus MgOH2 solid goes to. All right. So I like to just write my water. I know it's going to make water. And then I need to add a salt. What's my salt? Take your cation from one and your anion from the other. So I'm going to make MgNO3. But now I have to worry about writing my formula correctly. What's my charge if I have Mg? What's my charge on Mg? Plus 2. What's my charge on NO3? It is -1, and you can cheat. You can kind of cheat. If you have HNO3, I know that hydrogen's a +1. So in order to make this formula correct, NO3 also has to be a -1. So you can kind of, I call that cheating, but it's not really. Just being smart, right? Okay. So how does that change my formula? If my Mg is a 2+ and my NO3 is a -1, how does that change my formula? Remember, you got to crisscross your charge. Of 2 NO3s. Remember those skills that you learned? They never really go away. All right, my last question to you is this balanced? It's not. It's not. So what are we going to do to balance it? Try to balance your polyatomic ions first. So I have 2 NO3s. How many on the product side? I have 2 over here. So how many do I need on the reactants? 2. So I'm going to put a 2 there. Now that gives me 2 hydrogens here and another 2 hydrogens here, so 4. So how many hydrogens do I need on the other side? 4, but I only have 2. Am I balanced? Yeah. If you balance your polyatomics, it kind of makes it easy. Okay. All right. B, HCl plus NaHCO3 yields. What are we going to make? We're going to make water and a salt, and what else? Be careful. What do I have? Carbon. I have carbon. So I'm going to make my salt. How do I make my salt? I need my cation and my anion. So I'm going to make NaCl. And then what else am I going to make? I have carbon. I'm going to make CO2. Am I balanced? Yes, yes, I am balanced. Okay. All those balancing skills. Keep using them. All right, let's do another one. H2SO4 plus NaOH yields. I know I'm going to make water and a salt. I just got to figure out what's my salt. So I'm going to pull my cation and my anion. So I'm going to make NaSO4. Are my formulas right, and am I balanced? So first thing is check your formulas. You know the formula for water is right. So how about NaSO4? It's not. It's not. So what was my little cheat trick, right? I come over here and I look. I know hydrogen is a +1. So what is SO4 if I end up with a 2 down here? I must have had a -2. So you could do that, or you could go to the polyatomic ion table and find it. Either way will get you the right answer. So if I have SO4 that's 2-, and I have sodium, what's the charge on sodium? +1. So what should my formula be? Crisscross them. Na2SO4. Good. And am I balanced? I'm not balanced. My polyatomic, I only have 1 and 1. But what's not right? My sodium's not right. So if I put a 2 here, right, because I have 2 over here, so I put a 2 over here, now what? What's that? My hydrogen and oxygen. Okay, so what do I want to do? I thought you just couldn't, hold on. I thought you just couldn't use subscripts. So you have to determine the correct subscripts for the ionic compounds that you write. You have to put the right one. You can't just change them willy-nilly, but you do have to crisscross your charges to get the correct subscripts. And that's what you do to write the formulas, and then to balance the equation. Then the only thing that you can change is your coefficients. Yeah, yeah. Okay, so what are we doing? I need what? I need 2 in front of water. And it kind of makes sense, right? Because if I have 2 OHs, right? What is water? Water is HOH. So if I have 2 OHs, right? Where do my other hydrogens come from? Come on. Where do my other hydrogens come from? I have 2 here. So that's an H and an H. So I'm going to make 2 waters. You can think about it whichever way works for you. And then, oh, and don't be like Dr. B and put your states of matter on all your substances, okay? All right, B, HBr plus LiOH S. So I know I'm going to make water, and I know I'm going to make a salt. So I'm going to pick up my lithium from my lithium hydroxide. I'm going to pick up my bromine, LiBr. So are my charges, did I do my subscripts correctly? Yes, they're both +1, -1. Lithium's +1, beryllium, boron's -1. So bromine, not boron, bromine. So now I need to know, am I balanced? Yes, I'm balanced. That one was easy. But go ahead and write in your states of matter, Dr. B. Jeez. Okay. All right, now we're going to talk about chemical equilibrium. All right. So remember our discussion however many chapters ago when we were talking about equilibrium? And remember we talked about the basketball court and we talked about the players on the bench, right? You remember that? So if this is the, let's say this is the bench and here's the court, right? C-O-U-R-T. All right, so when I reach equilibrium, do I have the same number of players on the bench as I do on the court? No. Remember we said this was a no. We said that when we reach equilibrium, the things that are equal are I have the same number of players leaving the bench to get to the court as I do those leaving the court and getting to the bench, right? So we equate that to a chemical reaction. So if the bench is X and the court is not X, come on, the court is Y, right? So when we reach equilibrium, we have an equal amount of product and substrate being made. We don't have equal concentrations, but we have equal rates of reactions forward and reverse, right? So the arrow on top tells you you're going in the forward direction, and the arrow at the bottom tells you we're going in the reverse, right? So can we put this into a statement? When does a reversible reaction reach equilibrium? When the rate, right? It's not a concentration, it's a rate. Number of players leaving the bench per time, right? And number of players leaving the court per time should be the same. So that's a rate. So when the rate of formation of products equals the rate of formation of what? Reactants. So if we don't have an equal concentration of products and reactants, what could we say that we do have? We can say we have a constant concentration of products and a constant concentration of reactants, right? Because on the court, how many players can you have on the court? 7, right? I'm not a sports. 8? I don't know. Let's say 8. Say 8, right? We can only have 8 players on the court. And once the game starts, if you're not on the bench, you can't be in the game, right? So let's say they have 25 on the bench. Is it 5 per side? Golly, I was off. Okay, thank you. So you can have 5 on the court for the whole game. You have to have 5 on the court. And whoever's on the bench, that's how many you're going to have at the bench from the start to the end of that game. So is 25 equal to 5? Absolutely not. But for the whole game, you have a constant concentration of players on the court and a constant concentration of players on the bench. So you'll have a constant concentration of products and a constant concentration of reactants. Yeah? Okay. All right, so we can express this constant ratio of concentrations with what's called an equilibrium constant expression. And that's K, right? So in general, when we write K, it's the concentration of the products over the concentration of the reactants. What if I have more than one product? This would be like product 1, and then you would multiply times the concentration of product 2. If I had 2 reactants, that would be reactant 1, that's reactant 2. Right? Does that make sense? Okay, so let's look at our first one. We know that these are the what? Products or reactants? Reactants. These are our products. Okay, so if I'm going to write a K for this, K is equal to, I need to do products on top. Now, one thing that you do have to worry about, you're going to write everything that's a product unless what? You don't include solids, so they're in little parentheses S, or what? Liquids. Think about it, if it's to have a concentration, you have to dissolve in water. If you're solid, are you dissolved in water? No. If you're a liquid, are you dissolved in water? You're not. So you don't have a concentration for either of those two things. Okay, so just be careful of that. Okay, so I'm going to do my products first. So I have NBr3. What else do I have to worry about? I have a 2. What do I do with this 2? Coefficients become superscript, SUP, superscripts. So NBr3 squared. What are my reactants? I have N2 and I have Br2. Am I done? No, I'm not done. Because why? Because I have a 3, so that 3 becomes a superscript.
Thank you.
All right, B. So this one was A, here's B. Okay, so B. I have CO2, so K is equal to concentration of CO2. That's my product. Now I'm going to come over here to reactants. What do I have to recognize? I have a solid, so I'm not going to include my solid. It's a part of the reaction, but it doesn't factor into the equilibrium because it doesn't have a concentration. Okay, so concentration of O2. Am I done? Yeah. Try to throw y'all for a loop every now and then, you know, just for fun. Okay. So for the following values of K, indicate whether the products or reactants are present in larger amounts. You could memorize it, but you don't need to. Okay? What you need to remember is this simple formula. K is equal to products over reactants. And you already have to know this, right? So if I take my products and I say I have lots of products, lots and lots of products, that means that that value is going to be really big on top, that my numerator is going to be big. So I'll be dividing by a small number. So like 1,000 divided by 5, right? Am I going to get a number that's greater than 1 or less than 1? Greater than 1, right? So here, K would be greater than 1, right? Because I have more products. The reverse is true if I have more reactants. Let's say I have lots of reactants. What's going to happen to my K? Like, what if I had 5 divided by 1,000? I'm going to have a really small number. So K is going to be less than 1. So I'll have more reactants, right? This is like 5, no, I did that wrong. Come on, eraser. This is like 1,000 divided by 5, right? That's going to give you something big. K is going to be greater than 1. Or here you have 5 divided by 1,000. That's going to give you something small or something less than 1. Okay? So 1 times 10 to the 7. 1 with 7 zeros. 1, 2, 3, 4, 5, 6, 7. Is that a big number or a little number?
Big.
That's big. So tell me, do we have more products or more reactants? We have more products. So this is more products, right? You have a bigger number on top. If you have a number greater than 1, that means your P, your value on top, is going to be really big. 0.0045. This is small. So how do I get a small K? More reactants. How about, wow, 0.000079. Big or small? That's a small K. How do I get a small K? More reactants. Okay. Let me ask you one that I want you to be careful about. What if I gave you one, excuse me, and I had 1 times 10 to the negative 7? That's really small. You have to remember that a negative exponent gives you a really small value. So this would be a small K. So you would have more reactants. If I could, reactants. Okay. Yeah. Be careful with those negatives. They can throw you for a loop. All right. This one I really like. I think this is fun. Okay. So you got a reaction and it's going on, right? And it wants to hang out at equilibrium. What you have to remember is that every single reaction wants to hang out at equilibrium. If you left it alone, it would eventually find its equilibrium. But you know us, we can't leave anything alone. So we're going to stress our reaction. We're going to alter it in some way. And whatever you do to the reaction, this is like Newton's laws, you know, like every action has an equal but opposite reaction. Y'all know that, right? So it's the same sort of thing in chemistry. If you do something to a reaction, the reaction is going to have a reaction and it's going to try and reverse what you did to it. Okay? So if I have this reaction, I want to know what's going to happen. Is it going to shift in the forward direction? So is it going to shift this way? This is forward, or a right shift? Or is it going to go in reverse and have a left shift? Okay. So We're going to make some changes to our reaction and see what happens as it tries to get back to its equilibrium. So I like to do a little table, and I can say what we are going to do, what do we do, what does the reaction do, and then that's going to give us some kind of a shift. Okay, and we're going to figure out what that shift is. Okay, so we are going to add iodine. What are we doing? Are we adding a reactant? Are we removing a product? What are we doing? What is iodine? Iodine's a what? Iodine's a reactant, right? A reactant. I minus is a reactant. So we are going to increase a reactant. The reaction is going to have an equal but opposite pushback. So if we increase the reaction is going to want to decrease the reactant. That will get it back to equilibrium, right? The whole point is to get it back to where it was before we started messing with it. So if I want to decrease the amount of reactant, am I going to go in the forward direction or the reverse direction? If I want to decrease the amount of reactant, I want to get rid of I need to go and make product, right? So this is going to be a forward or a right shift. Yeah. Okay. What if I heat the reaction? That's what I am doing. Where's heat on the formula? It's a product. So we're doing something to a product. Am I increasing the product or am I decreasing the product? I'm increasing the heat. So what's the reaction going to do? Equal but opposite. Decrease product. How do I decrease product? I'm going to shift to the left. So I'm going to go in the reverse or left. L-E-F-T. A left shift. Okay. Remove lead to iodide. Where's lead to iodide? Right here. It's a product. Am I decreasing or increasing it? I'm decreasing it. So the reaction is going to have an equal but opposite reaction. So we're going to increase, it is going to increase the product. In order to increase product, are we going forward or reverse? Forward. Or a right shift. Okay, here's a little bit of a tricky one. Cool the reaction. Product or reactant? Product. Heat is a measure of temperature. So always, always, always think about that. So this is a product. Now, are we increasing or decreasing that product? We are decreasing the heat if we cool the reaction. Okay, so the reaction is going to have an equal but opposite. So it's going to increase the product. And what do you get? Forward. To the right shift. So always remember, the reaction will do the opposite of what we do to the reaction. Okay. All right. Let's just do these real quick, and because they're not in the back of your book. So if you add heat, which way are you shifting? You're going products. So this is a right, this is forward. Lower the temperature. Reverse. Reverse. So this is left, reverse. Remove CO2. If you write out the whole way to do it, it'll make more sense. If you remove CO2, you're removing this one, you're going to do a right shift. Okay, and then add water. That's another right shift forward. Okay. That's it, you're done. All right, we will pick up here where we left off on Thursday, and we'll do everything that we can. And I hope y'all have a great afternoon. If y'all have questions, let me know. And go vote. If you have not voted, go vote.
Can we just email you about chapter 8 homework?
Yep, just send me an email. I won't remember if you don't send me an email. It's a weakness, I know, but.
I wouldn't remember, and I have no secret. Last time I had 3 at home.
Yeah, it's all good. Okay, if y'all need anything, send me an email. Y'all have a great rest of your day.